Hi, welcome to CEE122 Week 5 presentation. So today we will go through the solution of the homework 4. The first problem, 3.70. The plane rectangle gate can pivot about the support at B for conditions given. Is it stable or unstable? Neglect weight of the gate. Justify your answer with calculations. So we have the pivot at this B point. If the pressure force provided by the water is acting on this B point, then we consider this system as stable because the force will not create any torque. However, if the force is not at the pivot, if it's on the top, then we'll push this beam to downward, clockwise. On the other hand, if the force is acting on the bottom part, then it will create a counterclockwise torque to this pivot, so the system becomes stable. So what we really want to find to prove this system is a stable or unstable is actually try to find YCP. Try to find where is the location of the pressure force. So when I denote, just to clarify, the Y here is a location along this beam. Okay, so it's not the depth, it's the location for this beam. Okay, so if you remember that the YCP for the open surface water beam, like this one, is at 2/3Y. So it's something somewhere at here. So if you know this relationship, the Y equal to 8 divided by sine 45 degree, then you have the solution. Okay, and Y equal to 8 divided by sine 45 degree is because we have the vertical depth is equal to 8 meters, and we have 45 degree here, and this length of the beam is equal to Y, so we know Y sine 45 is equal to 8, so Y is equal to 8 divided by sine 45 degree. Okay, and that's here. But assuming that we don't know this relationship, how can we derive this equation here? So the equation that provided by the textbook is actually this one. YCP minus Y bar equal to inertia divided by Y bar divided by A. This is the equation that we have. So YCP is equal to Y bar plus I bar divided by Y A. Okay, and Y bar is the center of this beam, right? So it's equal to 1/2Y. And we plug that into this equation, so it's 1/2Y plus, and I bar here, we will use inertia for the rectangle sheet. And the equation for this is BH to the power of 3 divided by 12. And you can find this equation in the appendix. But here I will just provide you. So this here. So you plug and the h here, this is the h, which is equal to y. So this essentially is b y power of 3 divided by 12, and this part is b. The width of this place is b. Okay, so we can plug that here. Divided by 12. And y bar is 1/2 y. The area of this plate is y times b. Y times b. Okay? And now we can reorganize this. B, we have both in the numerator and denominator. We cancel it. Cancel y, this 2 power of 2, and cancel y again to the power of 1. And 12 divided by 2 is 6. So we have plus 1/6 y. This gives us here, and then we divide by 2 for both numerator and denominator, and it's become 2/3y. Then we got the same equation as what we proposed in the very first at the beginning. So again, we know that y is y 45, and we know the depth is equal to 8. So y is equal to 8 divided by sine 45 degree. So YCP is equal to 2/3 y times 8 divided by sine 45 degree. And this gives us the value 7.54 meter. And if we calculate 8 divided by sine theta, which is equal to y, then it gives us 5.67. Okay, so if we minus CP, if we calculate sorry, I made a mistake. Is 8 times square root of 2. This gives us 11.31. So y minus YCP, 11 minus 3.54 is equal to 7. Minus 7.4 is equal to 3.77. Okay, so what this actually mean? So the length here, the YCP, assuming this is YCP, and the length here is equal to 3.77, which is larger than 3.5 meter that we have here. So we know that the CP is not at the location of the pivot. So we can conclude that the system is unstable. Okay, So for this question, you basically need to calculate the YCP. If the YCP is acting on this pivot B, then the system is stable. Otherwise, it's not. Oh, sorry. Let me correct this. Because we have a fixed point at A. Not a fixed point, but we have some barrier at A. So if the force is acting in this area, then the system is stable. But if the force is acting above the pivot B, then it will open this gate. Okay. Now let's move on to the next question. Okay, so in the problem 3.91, we have the hydrometer shown sink 4.7 centimeter in water. The bulb displays 1 cubic centimeter and the steam area is 0.1 square centimeter, and we want to find the weight of this hydrometer. So basically, we will use the relationship that the weight of this bulb will equal to the force provided by the buoyance. Okay, so the buoyance is equal to the volume times the specific gravity of water, because we have water inside here. Okay, so let's do it. The volume for this sphere is equal to 1 cubic centimeter plus the area of this tube that's sinking below the water, that is 0.1 square centimeter times z, and z is equal to 4.7 centimeter. Okay, and for low water, we know the gamma W is equal to 9800 Newton divided by cubic meter. So we need to first convert the unit of this cubic centimeter into the cubic meter. So to do that, we need to times 0.01 to the power of 3, because 1 centimeter is equal to 0.01 meter. Okay, then we times the gamma. Okay, 9800. Then we have that the value is equal to 0.0148 Newton, and this is equal to the weight. So we got our solution. Fairly straightforward. Okay, so let's move on to next one. So the problem 4.14, water flows in passage shown. If the flow rate is decreasing with time, and the flow is classified as A stable, B unstable, A steady, B unsteady, C uniform, or non-uniform, and we need to select that flight. Okay, so how do we distinguish whether the flow is steady or unsteady? What does steady mean? The steady means that the flow will not change with the time. However, the problem is already told you that the flow rate is decreasing with the time. So basically, it tells you that the flow is unsteady. And what is the definition for uniform flow and non-uniform flow? So the definition for that is that the flow line, the string line, has to be parallel in order to be the uniform flow. But according to the figure that we see here, those string line or flow line does not parallel to each other because it goes up and a little bit till down here. So from that, we can tell the flow is non-uniform. So the water flow here in this tube is unsteady and non-uniform. Great. Then we can move on to our last problem for this week. We need to classify each of the following as one-dimensional, two-dimensional, or three-dimensional flows. And before doing that, let's quickly review what's the one-dimensional, two-dimensional, and three-dimensional flow. So here's the figure that provided by the textbook. A is one dimensional flow, okay? Because we use the radius system and the y, so the flow is just going this way. However, if it is not a tube, it is not a circle for this tube, then we cannot use the radius system to describe it. So instead, we will use this XYZ system, and the flow become the 2D dimensional flow. Because as you can see in this part, we actually need X and Y to describe the location of the flow. And the last part, you can see that for this area here, it's actually changing along this z-axis. So to describe the flow, we have to use the 3D. The flow is the three-dimensional flow, okay? Because the velocity of the flow depends on the location x, y, and z. Okay, and for the B, the flow rate is only depends on the x and y, and for the figure plot in this A figure, the flow rate is only depends on the radius. Okay, so if we have this concept, let's go back to our problem is try to identify with in different conditions whether we should use one dimensional or two or three dimensional flow. Okay, let's see the first one. Water flow over the crust of a long spillway of a dam. So we know the spillway is usually look like a channel, but that channel I have bad drawing, but you get I try to draw a channel look like this one. So it's not a tube, so it's not one dimensional, and we assume that the flow is uniform in this channel, so the channel didn't the cross section of the channel didn't change along the y-axis. So in this case, we will consider the water flow is a 2D water flow. Oh, let me write that front. Okay, 2D, two-dimensional. And for the B, the flow in a straight horizontal pipe, and we assume that this pipe have a circle shape, so it's like this, and it basically is the figure that we have in the textbook here. So this will be one dimensional flow. Okay. And C, the flow in a constant diameter pipeline that follows the contour of the ground in a hilly country. So follow the contour, that means they didn't change the elevation of this pipe, and we already know that is the constant diameter pipeline, so it's still seems like this one. So we can still use the radius to describe the flow rates inside this pipe. So we will classify this as a 1D flow. Okay, to the D, the airflow from a slit in a plate at the end of a large rectangular duct. So it already tell you that this is a rectangular duct. So if you compare to these three situations down here, this will point to the situation of for the second figure that we have here. So this will be 2D flow. And airflow for the E, the airflow past the automobile. So assuming that we have a automobile here, and the airflow will flow through here, flows through the side, flow through the bottom. So it's not only have the different the velocity of the airflow, it actually depends on X and Y location, right? And also, if we see from the front of the car, it will expand to the side and go back. So it will also depends on the coordinates at the z-axis. So in this case, we need to we will classify the airflow to be three-dimensional. And similar for the eighth, we have a house here, and we have a airflow past the house. We'll go on the side. Okay, going on the other side. So the velocity also depends on x, y, and z. Okay, because the air, you can see that air like expand as it move on to the z-axis. This is also 3D. And for G, the water flow past a pipe that is laid normal to the flow across the bottom of the wide rectangular channel. So we can turn this. Hey, I couldn't draw on it. Let me see what happened. Okay, let me try it again. Okay, now I can draw it. So we have a wide rectangle channel here. And we have a pipe line normal to this channel, and we want to classify the flow path through this pipe. So essentially, because the cross section, we assume that the cross section of this rectangular channel is a constant. So even though we have a pipe here and the flow rate change here, but everything can be described by using xy value, just to describe the locations of x and y, because we only care the flow rates on this cross section that have a pipe. Okay, so again, if we see this statement like what we draw here, we can classify it into 2D. But as we go through all these different situations, we make our assumptions to classify flow for 2D, 1D, and 3D. But if you have different assumptions, this answer might not be the only answer you can use. So try to understand the fundamental definition of what is 1D, 2D, or 3D flow. Then you can better apply it to the assumption that you made. Okay, so this will be our last problem for today's recitation. Thank you very much.